if I give exercise, I should be able to solve them. So the goal of today's lecture is to work out one exercise from yesterday. For the huffling, I'll try to do as much as I can about it. Okay, that will occupy most of the talk, and it is really meant to be illustrative of a more general situation. So I'm really trying to go into the details. So first of all, let's set the record completely straight. I think I said everything I needed except I hadn't mentioned the Maslov potential. So the general situation was given a Lagrangian lambda, we name this category sheaf sub lambda of R2. Given a Lagrangian filling, the intuition is you will get a sheaf, and conversely, I would advocate any sheaf comes that way. Results on that. So when Yuan's lecture yesterday did mention that a lot. Again, keep in mind intuition that the endomorphisms of the sheaf are capturing in a way the cohomology of L. And today's idea is let's maybe, instead of focusing on the category to begin with, which is a lot of ohms and so on, let's at least try to understand the objects. And those objects actually will form some kind of nice geometric space that as the week keeps evolving, I will mention a bit more. But today the idea is, can we just name objects in this category, try to classify them all, or at least all of those that are reasonable enough. Now, this geometric space is going to have a lot of components. So your topology, think of connected components. This is an algebraic space, so it's more like irreducible components. And I'm just going to focus on the simplest possible one I know, which is already very interesting. And the two conditions that I'm going to impose, so I'm going to study those sheaves that have two conditions. The first one is the stock outside is going to be zero. So if I'm studying here, I'm going to ask that outside in the unbounded component of R2, give a complex Lagrangian, that is zero. It's an acyclic complex. Now, the second thing I'm going to ask is that the microstock, so if you remember, that's what I wrote there, when you have this map in the exodromy presentation going from here to here, the cone of that map is what computes the microstock. I'm going to ask that microstock is exactly K in rank. So those are called simple sheaves. But actually, since we're having complexes of vector spaces, you actually need to specify a degree. The way you specify a degree is you fix a Maslov potential on lambda, and then you require not only that the cone, that the microstock is concentrated in K, but it's also in the degree given by the Maslov. So for instance, if you have a Maslov potential, you should think of it as two conditions. It's on the one hand just K and also concentrated in that degree. So if I have Maslov potential 0 in this arc and Maslov potential 1 in this arc, then the map is going to go from having 0 stock outside, and now I'm forced to increase by exactly 1. So that's going to force me having K in here in degree 0, because the cone of that is exactly K with 0 shifted, but that doesn't contribute. Note, nevertheless, that if I had K here and I'm going through 1, now the cone is going to have to be concentrated in that degree. And then what I'm going to have is that up here, I'm going to have K plus, I need to increase in rank. So this needs to be total rank 2, but it's going to be total rank 2 like this, really being the complex 0, K, identity, K, 0. So that actually is the acyclic complex. So the idea that we go from K to 0 is kind of misleading. You go from K to a rank 2 complex, total rank 2 complex, which happens to be quasi-isomorphic to 0. Okay, so that's why we kind of go down when the Maslov is 1. Very quick comment. Okay, is anybody not familiar with the Maslov potential? And you're absolutely in your right to not be familiar with that. Okay, everybody's happy? Okay, just remember. So for a knot, it is unique. And the way you can specify it in a front is you start somewhere here, you say 0, and then every time you go up a cusp, your number increases by 1, up a cusp, increases by 2, but if you go down a cusp 1, keep going down, and then you go up to 0, okay? But if it is a link, there is an interesting choice. The numbers, I'm going to typically take rotation 0 people, so those numbers make sense in Z, but for a non-zero rotational Lagrangian, you need to do that. And the last comment is, for a link, you have many choices. So that's one of the things that yesterday was fun. So here you could choose 0, 1 for this component, and here you could choose anything else. Here you could do like 0, 1, 0, 1, and there are choices. And one choice that I will make today is I'll study the case 0, 1, 1, 2. If you choose another Maslov potential, that's fine. You're going to get another piece of the category associated with that Maslov potential. And now, very, very quick comment for the DGA people. Remember, when there's a link grading, and so there's also a choice over there. Okay, so it's exactly matching that idea. And now everybody computes the DGA always with the same link rating, but you could go crazy and take very crazy link rating and see what happens with that DGA. All right, are we okay so far? Okay, so my homework today is to work out in as complete detail as I can the hop link. So there's many ways to present a hop link. I'm going to start by one which makes it easier from the perspective of computing objects, and then I will change and make it the one that's not so easy. But we want to really examine the thing as thoroughly as possible. So we start with a hop link presented like this: 1, 2, 3, 4 crossings, and I'm going to close it up. Not with a rainbow closure, we're going to close it up with this kind of twisted closure. We call the -1 closure. So this is a -1 closure. The -1 indicates that the framing is twisting exactly by -1 when you do that. And the braid here is the braid sigma 1 to the 4th. And this guy lambda is a hop link. And it's sort of the most standard hop link that you can think of. The boundary of the zero section and a fiber in is styrofoam R2. Okay, so we want to study sheaves here. Now, the sheaves I will be studying are those whose stalks are finite dimensional complexes of vector spaces and they're bounded. So for those who know these words, it's not just all perfect objects, but pseudo-perfect objects. So, okay, so what have we learned? In the exogeny description yesterday, we knew we had to specify vector spaces in all these stratum, K, 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 K here, and then we had K squared here, and then you go down and this is going to be K and 0 outside. And now the poset is such that we need to specify maps this way. And then there's also going to be a map specified this way and then the map outwards. So all it is now, it's a problem of representations of this square, representation of this poset. And the constraints on the singular support are saying those two maps, this crossing is saying this map and this map, thought of as lines in K2, in the plane, they're transverse lines. They're not the same line. So what we immediately got from the get-go was that the moduli of sheaves on this Legendre in here, on this hop link, it will be something like tuples of 4 lines, L1, L2, L3, and L4. Let me write it for a second. It's like 0.231. And then such that Li is different as a 0.31, so a different, not the same line here. This is understood cyclically. So the first one is also different from the last one. And all of that had a choice of identification of the vector space. So you got to mod out by GL to K. Okay? So just to be very, very explicit, what we're saying is L1 is the information of this injective map. L2 is the information of this injective map. So maybe it makes sense to write notation like that. L3, L4. And they're like, what about this line? What happens is that if you compute this line, you get that this crossing and these two caps give you the condition that this line is the same as the kernel of this line. But now this is symmetric, so the kernel of this line is the same as this line. So what this will tell you is that this fifth line, that appears to be a fifth line, is actually identical to the first line. And now the first line had to be identical to L2, so that's why the cyclic condition of the crossing. Does that make sense? So the first two are transfers because of this crossing, the second two are transfers because of this crossing, the third and the fourth are transfers because of this crossing, and the fourth and the first are transfers because of this crossing. Because this crossing, but then really it's not. All right, are we comfortable with that? Okay, now this is really exercise session, right? So can somebody compute the dimension of this? And K is C if you want, like favorite field characteristics. So let's do a count. Okay, so this is dimension 1, right? And now I'm just choosing 4 points, so that's dimension 4. These are open conditions, don't change the dimension. And these are 2 by 2 matrices, so 4 entries. The determinant not being 0 is an open condition. So the dimension of these is 0. You should be, I'm welcoming you to be absolutely comfortable with the fact that they're very interesting 0-dimensional spaces. Okay, any 2-dimensional surface that you have, if you mod it out by an action of a 2-dimensional Lie group, that has dimension 0, even if the action is trivial. Because then what you're going to have is the surface times point mod that. If point mod that has dimension -2, so dimension 2 plus -2, dimension 0. That's the world we live in 2025 derived stats. Okay, so that's dimension 0, but it is very interesting. Okay, so now I want to be very explicit about this space, really understand also sheaves and how to compute them and express them, so on and so forth. So I want to make an assertion. So for assertion here. is that consider X to be the subset of C2. So these are points X and Y in C2 such that X times Y plus 1 is different from 0. Okay? Are we comfortable with this space? So this is a kind of relatively nice space. This is an affine variety. I mean, the way it's presented is quasi-affine, but it comes from localizing something, so it's clearly an affine variety in here. And it lives inside of C2. Are we okay with that? It has an action. And since I'm going to do a K equals C and the following action of the torus, so I'm going to have a torus acting here. C star times C star action given by, so the first one is really easy. The first factor acts trivially, doesn't do anything. It's pretty okay. So first factor here, so C star times point, trivial action, acts trivially. And the second one is an interesting one, trivially, and now you're going to have the second guy acting. So here times C star here. Let's have a parameter here, tau. So this acts by tau applied to a point xy will be sent to the point x. I multiply by tau, and then I multiply by tau inverse the y. This action comes from somewhere. I could expand for a while of where it comes from, but it is an action that does exist in this space. And why is it a well-defined action? Well, it certainly acts on C2, just in general, but you want to make sure it preserves this condition. If I multiply x by tau and y by tau inverse, then this stays exactly the same, so that condition is set. Are we okay with that? So the assertion is that if you consider this affine variety and this torus action, then the modelized space of the Hopf-link, again, 0 outside, microlocal stock being concentrated in the Maslov degree, maybe I should specify the Maslov. Potentially it's 0 in the lower strands and 1 in the upper strands, and concentrated in degree K in rank 1, then this is isomorphic. And this is as affine, the right way to say this as stacks or as derived stacks, but just think of as affine varieties modulo something. This is isomorphic to X, quotient by T. And these parentheses just are a way for me to not feel bad about myself. Just the way we indicate it's the quotient stack. But the point is, it's not just any crazy stack. The thing that I want to emphasize is this guy is an affine variety, and this group is acting very nicely. So this is an algebraic group action. It's a reasonable one. Okay, it's not too crazy. It's not free. Action is not free. Maybe I should say that. So that makes things interesting. For the case of a knot, you're going to get free action. So this phenomena doesn't happen as much. You're going to just get a trivial action. But that's what we have. And the theme continuing today in Hoha's talk, and then me, and then tomorrow, is going to be that we're going to be studying things that are a braid, and then you close it up. And what I'm going to tell you is for those guys, these moduli are always of the form an affine thing modulo an action that I can write down for you explicitly. Does that make sense? So that's maybe a first hint that dealing with these moduli spaces is not too bad, at least for these positive braids. Are we comfortable so far? Yeah.
So what you're saying earlier, so when we wrote all the orange things there, right? So you got the 0 Ks, then the K squared. When you get up to K, that really should be a rank 3 complex whose homology is K.
Yeah, it will be the direct sum of the complex K in degree 0, and then K plus K shifted by 1.
I see.
And then the second term in that direct sum is a cyclic, so you're just going to end up with the first one.
I see. And then when we get up to the top, it's really actually a rank 4 complex.
Yes,
with homology
which is
0.
Direct sum of K mapping to K with the identity twice.
And is it always fine to just ignore that and just write the homology? And
well, that's why I say the words DG derived. So the DG category just means the arms are complexes, but such a complex would not be 0 in the DG category. In the DG category of complexes, that complex is not zero.
Hmm.
When we say the G derived, it's because we've localized in a way that all cyclic complexes are the object zero, or
Mhm.
isomorphic to zero. So it is legit to write zero in the sense that they're isomorphic in that category. Canonical.
Just about the dimension count at the top.
Yeah.
The action by GL2K, it has stabilizers, right? Like so it's actually a PGL2K. So would that be modded out by dimension 3?
You absolutely have a point, but like it's fine if you can act trivially, like a space and a group G. The space has dimension 17. You say the space has dimension 17. If G has dimension 14, the trivial action of G acting on X, you would say X mod G still has dimension 3. It's going to be the stack which is X times point mod G, and point mod G has dimension minus 14. It's a very good point. Yes, this is very important to understand. The stacks, there's a point to that. They're very useful. And one thing you can do is things like that. And it makes sense to work with very negative dimensional spaces because they're keeping track of that. And if it's trivial, it's trivial. That's perfectly fine. And indeed, one factor of this, which is what you're saying, is this is going to look like a one-dimensional space times point mod C star. But point mod C star is dimension -1, so that's still dimension 0. Does that make sense?
I think so.
Yeah,
Thanks.
okay.
No, I was just saying, just to be clear, the action of this trivial action by scalars on envelope lambda is exactly this trivial action of C star.
Yeah, well, I mean, I'm going to prove this urgent. And
Okay.
that's, yeah, but yeah, like, yeah, okay. So, okay. Are we happy with what the surgeon is saying? None of that. Now I'm going to explain why it's true. Okay. So this theme that these guys are going to be in a fine variety modulo and a nice group. Okay, so proof. So you have these 4 lines and you have the GL2 action. So by using the GL2 action, so by using not the entire GL2 action, but by using a piece of it, can assume, so we can assume and do assume that L1, the first line, is generated by the vector 1, 0. So when I write these, I really mean generated by. Does that make sense? And similarly, because L2 is different than L1, so I'm using this, that can be assumed to be the vector 0, 1. So this is your linear algebra exercise, so your undergrads and freshmen, that given any 2 non-collinear vectors in the plane, there is a linear transformation that brings them to any other GL2X transition. Now, I cannot assure that the third vector is going to be of a specific form. Rather, what you know is that the third vector is going to be different than this one. So all you need is any vector, any line, that is generated by something that's not collinear to this. So that does the job as long as I put a 1 on the top. It doesn't matter what I put on bottom. If I put 1 on the top, that's immediately not that guy, right? For algebraic people, we have the -1. We're in SL2, but you can ignore that if you're not an expert in Lie theory. Okay, so that is an example of that, right? And then the fourth guy, well, the fourth guy is going to be in a similar situation in that I want it to be different from L1. So I need a 1 on the bottom, and then I'm going to have some variable y in here. So given two variables x and y, I can name these 4 lines. And the way they're written, I already get that L1 is different than L2, that L2 is different than L3, that L4 is different than L1, but I still need the equation that L3 is different than L4. So then, L3 different than L4 says, and I'm really going to bring it down, that the determinant of this matrix -1 x y 1 is not 0, which is to say, I take IE -1 minus x -1, so that's 1 plus xy different from 0. And x and y here are arbitrary numbers in your base field. Does that make sense? So that, yeah.
So to get that equation, you needed to choose the -1 on the first and a positive one on this, well, on the third and a positive one on the fourth.
Yes. Oh, they're isomorphic. like, if I already put a -1 instead of a 1, you're gonna get an.
Oh, on the
N-1,
complex,
right?
sorry, okay.
Yeah,
Mhm.
they're complex now. I mean, okay, let's work on the complex.
Yeah,
numbers.
yeah.
This is a very interesting. Okay, so this is sort of part of the first assertion. Why this guy pops up is exactly out of this. Are we happy with that? Okay, now let's further understand this action. These guys were matrices 2 by 2, determinant non-zero. Now, what happens when I force these two guys to be here? What is the stabilizer that's left? So what's left from the GL2C action is, well, now you're looking for GL2 transformations that fix these two lines. That's exactly the Cartan torus. So that's anybody in the diagonal form, 2 non-zero entries. So that's exactly this torus acting in here. And now the way this guy acts on these lines is exactly the way, or it's isomorphic to the way, conjugate to the way in which this actually acts on here, which was what Lenny was saying before, that the actions do itself. So one acts trivially, the other acts in a non-trivial way. Are we okay so far? Yeah, so here there's two people acting, this C star component and this C star component. And they act on these lines just by acting in GL2. So you multiply this matrix in here and this matrix by here. What I'm saying is this action, okay, because they act on this and they preserve this condition, they act on this space. So how do you act by this matrix on this space? You think of X and Y as these two vectors, and it acts by multiplying by these things. Okay. Now what I'm saying is that action of K star squared or C star squared of the torus on this space of lines is conjugate, is isomorphic, once you do this isomorphism with X, to the action which is one factor acts trivially and the other acts by tau and tau a first Y. The non-commutative analog of that is much more subtle. It's some kind of conjugation, and then the diagonal torus acts trivially, but you're welcome to ask me about non-commutative place afterwards. Is this explicit good so far? Okay, so let's continue by really trying to understand this space and how it relates to sheaves and Lagrangian fillings, so on and so forth. So one way to think about this space, and this is a general thing I try to teach my students in grad class and everything. It's like, how do you study a space? So how do you eat bread? Well, you chop your baguette, right? So you take a space, you start taking hyperplanes, and then you study it. So that's what algebraic geometry does all the time by polarizing and taking like hyperplane sections and everything. So one way is to chop, and another way to think about chopping is you map somewhere, and then the fibers are the things that decompose. So one way we can study the space X is by, so this is 1 plus xy different from 0 in C2, is by mapping it somewhere. So we can map this guy down to C by multiplying by sending x times y. So and anybody you just project down. So what do you get? Well, the guy downstairs here looks like this plane in here. Say we have the origin in here, and here we have the point -1. All right. Now, what do you know of this space? Well, up in here there's C2. That's a big C2 space. That's the entire thing. And let's look at the fibers of this map. If I pick a fiber that's far away from 0, and it's not -1, what I'm going to have is this is some fixed number, say 7 or something, the way I wrote it, -7, something like that. Okay, so now when this is a fixed non-zero number, I can write y in terms of x. So that becomes graphical in one of the two variables. So then I get a sister action, right? And none of them can be 0 because this is not 0. So what I get is that above this fiber, I get exactly a copy of C star. So this is C star, which is exactly given by, if this is the value of alpha, this is the equation x, y equals alpha. And here alpha is non-zero. Does that make sense? This is what a C star looks like. A C star is a cylinder. It's like the plane minus the origin. You think of geometrical as a cylinder. C star is 1 if you simplify the electric vibrations. All right. Now, there is one fiber that is not there. So any other fiber actually looks exactly the same. So fiber here, C star. And there's one fiber that does not exist, which is the fiber above -1. So above -1, and that's why I'm writing it in this kind of dashed form. In this dashed form, this guy is not there, okay? Not there. Does that make sense? Because if this is to be non-zero, this guy can never be -1, so there's nothing that maps there. So everybody gets a pre-image, which looks like C star, except for -1 and 0. -1 doesn't get anybody, and 0 now we're going to study. So this, the way I usually call this thing, it's C2 minus a smooth conic, the smooth affine conic. All right, so what's happening at 0? At 0, I have a space which is X, so the fiber of these, the thing that maps over 0, it's going to be space of the form x, y equals 0, which you want to think, for instance, is a 2-coordinate axis is C2. And one way to draw sort of a smooth topology is the 2-coordinate axis, it's going to be like a cone like that. All right, does that make sense? So the point here in the middle would be the point 0, 0. And one of the other, so these two lines has the origin, and then one of the complements C star is going to be x different from 0, and the other y different from 0. Does that make sense? Because x could be different from 0, but if y is 0, you're still getting 0. All right, are we comfortable with this picture of x? Okay, so now how does t act? Well, the first component of t acts trivially, easy, you just do it, nothing's happening. So how does the second component of t act? So the t action, let's do it in black. So the t action in here, t action, the interesting one is think about the tau of xy mapping to tau of x, tau inverse of y, what we wrote in there. Well, what does this preserve? This preserves this quantity of this vibration, therefore it preserves the fibers, therefore this acts fiber-wise in here. So the t action actually is a C star, I mean, there's a trivial one, but the non-trivial one is a C star acting on this C star in here. And it does so in a free way. So this action in here is free in this fiber. It's free in any regular fiber over here, meaning it sends any point to any point. The reason is, if you act on C star by multiplying by a scalar, then by a scalar in the torus, then you can bring any scalar to any other non-zero scalar, right? Now, there's no action here, that's fine. This is the interesting action. So what's happening in here? Well, where does this map the origin? To the origin. So this 0, 0, it's a fixed point of the action. So this is a fixed point in there. And once I remove the fixed point, I'm left with two C stars. And now the action acts freely also on those two C stars. So this is fixed as 0, fixed as 0, 0. And free otherwise. So the action is not free because it fixes the origin, but once you remove the origin, the action is free. Does that make sense? Because this minus the origin is the union, this joint union of two C stars. Are we comfortable so far? Okay, now comes the fun.
So it's free, but not transitive. So it's transit on each of the components, but.
And free.
Right, free, but it doesn't interchange the components, or does it?
Oh, no,
Okay.
It fixes each component and it acts freely and transitively.
Yeah.
Okay, so what is a way to visualize the space x mod the action? Well, you go back to the basics, which is how do you define a quotient? A quotient by definition is a space of orbits, of cosets, whatever you want to call that, but it is an equivalence class, right? So now all we need to do is take equivalence classes of these orbits for this action. So, okay, now I'm going to stop writing C as a plane, and I'm going to write it as a line, if that's more comfortable for everybody. So I'm going to think of this guy on the bottom as parameterizing the orbits, except it's not exactly quite that. So I'm going to think of C at the bottom. This is C. Now, there's one orbit that shouldn't be there. That's the orbit for -1. So we remove -1 in there. So that's already C minus that -1 point. Now, any orbit of this action that is not the red guy, the whole thing being transitive, the whole fiber is an orbit. So when I quotient down, I get a perfectly nice point. So this is just really a point in the classical sense, a nice smooth point in a classical sort of algebraic geometry 101 sense. Are we okay with that? Okay, so what's happening with the orbits here? How many orbits do we have around here? So around here, we have, I don't know how to draw this legally, but like, this is one orbit, this is the other orbit, and then the other orbit is the wiggle guy, right? So here I have 3 orbits. Right? Now, so in these 3 orbits, it means that above this point, I should have 3 points. Now, 2 of the orbits go down to like kind of normal points. I mean, normal, this is already not Hausdorff. But if I didn't take into account the origin, what I would have is the affine line, topologize as usual, but where you remove a point, that's easy, and then you double the origin. So, I always felt when I taught base point topology, like point set topology, like it's useless, this example of R2 with a double origin. No, it's very useful. Like, it actually appears in real life. But then what's happening is that we also have the origin guy, and then the origin guy, and I really don't know how to draw it. It's another point, but it's like a funkier point. So it's a point that actually has stabilizer like C star, like one of the two actions, because it's fixed. Now, really, the whole entire thing has a trivial stabilizer. So x mod t is this entire space times point divided by C star, which, I mean, when we write papers in research, we call these BGL. Yeah. So the whole thing always has a trivial stabilizer. That's a trivial action. So this is from trivial action. And then we have this point, which has an extra stabilizer. And so this guy gets two stabilizers, this one and this one, and everybody else doesn't have a stabilizer except for the trivial. Are we okay so far? All right. Okay. Now, the important question in life. Where is my Legendrian? Where are my Lagrangians? Okay. This is supposed to parameterize some kind of Lagrangian fillings. Where are they? Oh, start thinking. Okay. So let's consider the fillings. So consider the fillings L0, L0.5, and L1 of lambda as follows. So what L0 is going to be, it's going to be, we're going to play this game. So now use the moves from the first lecture. So we locally have this braid with 4 crossings, right? So we're going to build it as a movie. And the way we're going to build the movie is this guy will go down to something that has 3 crossings, where the first thing we do is we've collapsed these first 2 guys into 1. So in this first we do this one, and then we collapse this extra 2. So now I continue here and I collapse this extra 2 using the d4 minus move. So this is d4 minus moves that I like so much. Minus d4 minus. And now we're down to this. But the -1 closure of this is an unlink. So that gets immediately filled uniquely by 2 disjoint Lagrangian disks. So that's our filling L0 in well. Okay, now filling L1. So filling L1 is going to be similar, except that we're going to use slightly different. I'm still using blue. And then so now I'm going to keep these 2, but the first time I do the pinching, I'm going to keep this one. So these 2 guys are going to become 1 crossing, and then I still have the extra crossing in here, and I still have the extra crossing there. So in this one, instead of doing these 2 into 1, I do these 2 instead into 1. And then after that, I do these 2 into 1. Does that make sense? Then I go through the link, and then set. So that's the filling I'm going to call offshoot. Fully messed up color coding. Color coding is this, and then it continues, and then we match this. The color coding. So this should be in red. This was red. So this is red. This is red. This is orange filling. This is blue filling. This is a green filling. So here. And now, who wants to guess what's the other guy? Or which color does the other guy go with? The other guy was in color red. So the other guy, which is L0.5, is the filling that comes from, so it's filling by bounding a disk in each component. So by Lagrangian is D2 union D2 with an immerse point, D2 filling each component. One way to think about it is you could use a class move. And so if you do a class move, you would go from having 4 people, 1, 2, 3, 4, do a class move, say in these 2 pieces, and now you're down already to 2. So this will be a class. And now you're done again. So using the so I'm really trying to be legit in the sense that we said these on the first lecture. Those are moves that we can use. D for minus gives you these 2 ways of using D for minus gives you L0 and L1, and the class move gives you an inverse filling. Okay. There's a reason why I'm thinking of these in between these 2. To kind of recover these 2 points. All right, where are these guys in here? As one should be kind of. Where is the red guy? The red guy is here. So this is the inverse one. Okay. L point. Okay. So now how should we think about L0 and L1? Well, if you thought about like Benjamin's lecture yesterday, you were listening carefully. One way to think about it is, well, we don't only have the Lagrangian, we have a Lagrangian with the local system. So we're thinking of this Lagrangian filling, which looks like a cylinder, but it also is endowed with a local system. Now, a local system, it's going to be, because we're working with GL1, that's going to be something that is on from, well, pi 1 of the cylinder, but because it's abelianized, pi 1 abelianized, I'm writing H1. But please always take into account that when I write H1, I really mean pi 1 abelianized, because it's going to factor through here. And this is mapping, so this is local systems representing in this. Now, hopefully you teach this in an algebraic topology course. This is exactly the first cohomology with coefficients in C star. And in the case of a cylinder, that's just a C star. So what I'm looking for is not just a point here, I'm looking at an entire C star in there. Does that make sense? Anyone wants to take a guess? Okay. So this guy L0 in green, the C star that corresponds to it is going to be everybody here. Now I put the upper point, and now I continue. I have to skip that point, and then I continue. What is this? Well, this is the affine line. This is treated perfectly nice. It's like a nice classical smooth C star minus the point. That's their C star. And now I think we're all in shape. What is the orange guy? The orange guy is exactly the same thing, but now you go up the other guy. So that's how you see the 2 Lagrangian fillings. This sort of nice C star on the top, nice C star on the bottom. And you kind of see this guy who's like, even the topology is telling you that somewhat you should be able to recover, or this guy is really like, this is not Hauser. So like you cannot separate the green or the orange from the red. The red is, the topology is telling you the red is very importantly, very, very closely attached to both of them. Does that make sense? All right, good. So absolutely welcome you to compute the ohms of these guy and these guys. So that has cohomology in degree 1 and 0, and it's just K because it's cohomology S1, so it's the cohomology of S1. That's the cohomology of S1. This guy is much more interesting because you would say, oh, maybe I'm going to get the cohomology of the 2 disks, so I should get K and K, so K squared in degree 0, and that's it. But you don't get that, and that's maybe you can ask me why, but the shift gets you K squared in degree 0, but you also get K squared in degree 1. The reason is because there's a local system that you're not thinking about, which is D2, D2, but if you remove the origin, there's this local system, and that's a legal shift that gives you the right thing. Now, why this should be the case? Well, compute the Euler characteristic of this. What is the Euler characteristic of this guy? 0. What is the Euler characteristic of this guy? 0. Euler characteristic is the derived algebraic geometer's way to talk about dimension. So that's exactly fine. That you get Euler characteristic 0 because this is a stack of dimension 0. And a stack is said to be smooth if the Euler characteristic varies smoothly. It's essentially, what do you say is smooth in dimension 1? Or sorry, in like Guillemin polar. It's smooth if the tangent space varies smoothly, in particular, if it's always of the same dimension. So the notion of dimension for a tangent complex is now the Euler characteristic. So you want the Euler characteristic to vary. And indeed, the Euler characteristic is 0. This one is 0. And when you compute with the appropriate cheap local system, this also has Euler characteristic 0. It's K2 in degree 0 plus the K2 in degree 1 coming from the sheaves. So actually, this thing, and I know it doesn't look like that, this is a smooth stack. So these are really nice manifolds. I know it doesn't look, I don't know what it looks like. This is a perfectly nice 0-dimensional smooth stack. And in fact, any stack like that appearing in algebraic, symplectic geometry, they're going to be smooth because this category is smooth in a homological sense. All right, so this was what I would say, a reasonably thorough treatment of the Hovling via this front. Are we comfortable with that? So I wasn't going to do topology. I didn't really appreciate topology that much. And then in my master's, I just took this topology class. It was a requirement. And there was this teacher, Montesinos, who like absolutely changed my life and view of everything. And Montesinos, well, he taught me many things, but one thing he taught me is like how to like squeeze a lemon. And you know, so when you're working an example and you feel like, oh, I'm done, I've really understood it, I've done everything, then it's the time to continue. Maybe you can take a little break, take a walk, but then come back and like keep hammering. So you're squeezing the lemon, the juice is coming out, and then you don't want to go and 2 days later come back. The lemon is dried out, it's not good anymore. You want to just like take the moment and then keep pushing until the last drop is there. Okay, so that's how maybe I'd say that's one way I have learned a lot of math. It's by once you feel you're done with the example, you're actually not done. You're maybe only 50% there and you keep squishing. Okay, so what's one way to squish that is to say, now let's do all of this, but with a different front. And we know what the answer should be, and we should still be doing that. So if you're okay for the next 10 minutes, I'm going to squish the last drops of the half length. And then at the end, I'll generalize all of this.
I have a question. How do you see the stabilizer at the start point from the filling perspective?
How do I see this stabilizer from the filling? Yeah. Okay, okay. At some point, maybe we should have an informal discussion on the algebra geometry. But the answer is the cotangent. The cohomologies of these should be thought as tangent complexes. And a tangent complex in a derived algebra geometry is an actual complex. It's not just concentrated in degree 0. So when you compute the tangent complex of these, the tangent complex of these is going to be 0 k squared. Maybe I'll just give you the x guys. So x0 is going to be k squared, and x1, I'm just computing the cohomology. The cohomology of tangent complex is going to be like that. And the degrees are actually such that this is in degree -1 and this is in degree 0. So the stabilizer is coming from the fact that this degree -1 has an extra piece. So all of these people in degree -1, they're just going to have x0 equals k. And the difference is, so that's from the trivial action. And so when you compute the tangent complex of these extra guy is telling you there is some other stabilizer. That's actually there. I know this is maybe counterintuitive, but I've been trying to advocate for that. It might be counterintuitive for people to think that cohomology should be thought of as a tangent space. But that is what all evidence is pointing to. So in particular, LCH should be thought as a tangent space, as a complex. It's just not of an affine variety. It's just of a derived stack. But LCH are tangent spaces, and in fact, they vary smoothly. And this thing, k squared, is smoothly perfectly fine with k and k, which is what you have for that. Okay, maybe that's good. All right, so I'm gonna now study shifts. So here shifts were all clear to everybody, right? Like yesterday, maybe when we did the exercises, you were like, this is 4 lines, and if I specify that, I'm done. So now I want to work out the front that caused a bit of commotion yesterday, maybe because I didn't say anything about the mass law potential. But so if you take this Hovling and you isotope it in a way that you end up with a Hovling, which is just the unknot and a rep push off, the way the potential changes through that isotopy can be traced. And you get a potential which is not maybe the completely obvious one. So through the isotopy that brings this to this, there's more than one, but there is one. And the potential that used to be 0, 0, 1, 1 now goes to 0, 1, 1, 2. One way to think about that is somewhere in this isotopy, there is a Rademacher 1 that you had to do, and that shifted the potentials. And then there's a Rademacher 1 that you undid, and then that made the guy be 1, 2 instead of 0. So now you want to say, I should be able to see that space over there. And in particular, all those shifts that I see very nicely from lines in this example. So where are those shifts? Okay, so from this front, there are 2 classes of sheaves. So and this is a bit arbitrary, artificial, but 2 classes of sheaves. So I'm going to divide them like this. So the first type of sheaves, these are sheaves built these are built from from the following two. So they're built from the I sheaves. So they're built from the sheaf that is K here and 0 everywhere else, and the sheaf that is K here, well, K shifted by 1 here and 0 everywhere. So this is as stock K shifted by 1, and here it has stock K. And you can build sheaves out of these two. For instance, you can take direct sums. How we go with that? That's one way to build them. And then there's a second way to build them. And again, this is like the front. This is how much sheaf really see the front. Like it's very sensitive to the front. Another way I could do people that have that are people who are only concentrated in this region and only concentrated in this region. So these are, maybe this should be understood as an imperative, but let's build first. To build from, obviously, anybody familiar with rulings, this should be tickling your spidey sense. Have two switches. And you can also build from this guy on top, again, by 1, and then the other one on. Are we okay so far? So let me point out, neither of these two guys is in the category. Okay, but this is not to say you cannot use them to build people in the category. All right. So how do you do that? Well, the answer is you essentially take extensions. So you look at short exact sequences that have this on the two ends and ask what can go in the middle. Okay. So here you compute the extensions. So compute extensions of these two guys. Maybe let me call these two people, so it's going to be Q1, this is going to be Q2. This shifts Q1 and Q2, and then the extensions of Q1 and Q2, those are just going to be given by K. Are we good here? And you can think of this as sort of two kind of cases. Trivial extension, so K here means there's some factor alpha in here, some number. So the trivial extension is the one that corresponds to alpha equals 0. So the scalar being chosen to be 0, okay? And that literally gives the direct sum. So that's going to be Q1 plus Q2, which should not go with blue. Should give the sheaf that you get when alpha is 0 is Q1 plus Q2. So what does it look like at the level of stocks? Well, at the level of stocks, which again is not all the information, it's going to have stock K here, K shifted by 1 here, and here it's going to have the complex 0K, K0, but the map is going to be 0 here. So this is literally going to be K plus K shifted by 1, no differential. That is no true. Can anybody tell me what this corresponds over there? And you don't have to know any math. So, the red sheaf in here is this red point, it corresponds to the spilling. The direct sum of the two i's, that is the inverse spilling. Now, there are non-trivial extensions. So for a non-trivial extension, alpha different from 0, again, alpha understood as the parameter for the extension, you're going to get some sheaf, f of alpha, different from 0. And I want to point out that this has the same stocks as the previous one. So the same stocks as everybody in there. So again, a case in which you cannot just by looking at the stock that tell when the sheaves are apart. So this kind of twisted direct sum. Okay, so this guy in blue, for instance, I mean, one has to be careful with identification. That F alpha corresponds to the Lagrangian filling L0. And I want to emphasize, whereas in this presentation, L0 and L1 looked pretty much symmetric, like there was this kind of very natural C2 symmetry, which in a way it came from the symmetry of this kind of front. The symmetry here is maybe not so obvious. There are symmetries like this one and this one, but really the symmetry that is exchanging these two Lagrangian fillings is the one that brings this crossing around to the other one. And that involves a bunch of Rademeister 2s and moving about and coming about. So it's not so apparent. And maybe through that lens, it's not so dramatic that those fillings, L0, those sheaves that describe this filling L0 are very different than the ones describing the filling L. So here, you compute exactly the same extensions. if I had 5 more minutes, or maybe How can say a couple of things about that. You compute these things, this is very easy to compute. So you just take, so it's 2 sheaves you're computing are here, right? K and K. Ohms from 2 objects E to F, it's the same thing as E tensor F dual, right? So that's the same as tensoring this sheaf with the dual of this sheaf. Now the dual of this sheaf is very easy. The dual of this sheaf is just the same sheaf, but now the correlation go outwards. And why do I like tensoring? Because tensoring sheaves, you're just multiplying the stocks. So the stocks of these were 0 here, and the stocks of these were 0, 0. So what do we get? Again, that characteristic function of the intersection. So you just get a sheaf that has exactly K in this disk is now closed on both sides because we changed the orientation. So what is the global sections of that? It's the cohomology of the disk, which is K, this K. Okay, so that's how you compute X in real life fast. Okay, so similarly here, you can compute it to X. This is very slightly more subtle, but here the X are also the same thing. And here you end up seeing that the X is K, but something more interesting happens. It's essentially what's happening is the trivial extension is not in there. So trivial extension, like let's call this parameter beta now. The trivial extension beta equals 0 is not having the right singular support. So it's not a sheaf in here. We learned that from Casals lecture. When he took this guy and he took the direct sum, the singular support that you get is going to have like a whole arc of people in here, which are not in the front. So trivial extension is not allowed. So, I mean, you started with 2 things that were not in the category. If you do certain things, you might still not be in the category. But the thing that does happen, which is kind of nice, which is when beta is different from 0, actually that extension class f of beta should go in orange. So that guy should have gone in green and should go in orange, but f of beta, it actually is in the category. So any non-trivial extension in here does give you something that's supported in here. Well, and these are the guys representing the filling L1. In particular, if you did compute endomorphisms of this, or you did compute endomorphisms of that, you would get the cohomology of the sum. All right, and yeah.
What does the stocks look like in this last example?
Oh yeah, very good question. Thanks. So the stock in this last example looks like this. Looks like 0, K shifted by 1, and here it is the complex that you could say it's 0, but really it's the complex that appears. It's 0, K, and 0. It's 0. Stock is 0, and a cyclic complex. So the sheaf looks like this. Is that right?
Sorry, just can you kind of explain what's the difference between this and the far left when?
This is not an acyclic complex. This in here is the vector space.
Oh, sorry. When the alpha was non-zero. Sorry.
No, this has the same stocks as this one. Like, so here I'm taking the extension of the 2 I sheaves, and you end up with something that ends up having stocks like the same as this one.
Mm-hmm.
And here I'm taking an extension of 2 different sheaves, and the stocks in the middle end up being acyclic.
Mm-hmm.
So these 2 sheaves are already different at the level of stocks.
Mm-hmm.
What's not maybe so obvious is that if you just look at the stocks of this guy, you couldn't immediately tell him from this guy.
Mm-hmm.
All right, so that's my 5 minutes oversigned. Okay, so but this is kind of, does that make sense? And I have a time constraint, but if you want to really make lemonade, like pick now another front, maybe present the hub link as like a 3-stranded braid or something. Uncle did that, and where is Uncle? For his that was his own initiative. He decided to work out the hub link as a 3-stranded, as the rainbow closure of 1 to 1. And like computed all eggs and all everything in that case, and yeah, I thought it was great. Had a really nice table and all. Okay, so you can continue these sort of ad infinitum and identifying those spaces. But yeah, this is again an example where the sheaves are maybe not so obvious as they were in this kind of front projection, but we still get the same from it.
But for alpha and not equal to 0, can we throw arrows in each example?
Arrows in which sense?
Well, I mean, from chambers to chamber.
Like,
I mean,
what
they-
is the
they-
posset structure of this?
So the linear maps between complexes.
Yeah, I can, but can we do that like after? Because I need to introduce a definition, because otherwise I cannot do this. Is that all right? So yeah, we can do an exogenous description. That's a very natural way to continue. Okay, so the final thing to say for this lecture is to introduce a generalization of this space X, which was this 4 lines in C2 to any positive grade, and then House recitation will start working out examples for you that are slightly more general in the Huffling. Maybe he's planning to do trefoil, maybe something with 4 strands, that I'm at least define the space. All right, so by definition, we're going to consider only grades that are positive. That's because the front projection only allows for positive crossings. Positive here meaning positive in the least theoretic sense, not positive in the topological sense. There's no orientation. They're all over crossings. That's what's positive in algebra. So definition. Given a braid beta. So braid beta is going to be denoted with this braid. Braid group, I'm going to denote it BRN plus. That's the positive braid monoid. But actually the positive braid monoid, I'm going to maybe denote it somewhere else. These are literally words. So these are positive braid words. So when I write this, I have a specific word in mind. So we define the following lambda beta. So this is the Legendrian inside of the infinity of R2 by a front, by its front, and its front is going to be as follows. We're going to take the word beta in here. Now, this looks artificial for now, at least. I'm also going to add a half twist. So I'm going to put here double denote the half twist. This is to avoid a lot of problems. In particular, you might not have Lagrangian fillings. The moment you put a double unit and you require that beta kind of has double unit inside, or it's like demonstrator product is double unit, then it does have fillings. And then we're going to close it up with a -1 closure. So we're going to close it up like this. And dot. Does that make sense? So this is the braid that I'm going to be, this is the legend that I'm going to be calling lambda beta. Right? So this is the first definition. Now the second definition, hopefully through the example that I've worked out, you see where we're going now. Second definition. So these are again that we call positive braids, and it's called braid variety. X of beta is defined to be the following variety. So it's tuples of flags. There's going to be F0, F1, dot, 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 F to the length of beta. So these are flags. I don't have a better way to talk about flags than saying this is G, the Lie group. So the notation here is G is the Lie group, GLN, B is the Borel. So these are upper triangular matrices, and then G mod B is the least theoretic way to talk about the flag variety. So this is the kind of legal way to talk about it, but just think about flags in the vector space Cn, and then such that the flag Fi is in relative position as J, S, J, S, Ij, with respect to J plus 1, if the word for beta were sigma I1, dot, sigma I. Okay, so that's what this guy is. Okay, well, I'll have to add a couple of things. All right, let me just draw a picture so we're on the same page. So take a 3-stranded braid, something like that. Okay, so this is my beta for now. So now remember how we thought about sheaves. You said 0, k, k squared, k cubed. So that's sort of a line within a plane within this figure. Now, when I pass the first crossing of beta, here's my sigma I1. What I want is that the new flag is exactly going to have same K, so that K is gonna be the same as the previous K. This plane is gonna now be different because we're passing through the crossing, and the K3 is gonna be different. So that's all I'm saying. This is just trying to say, pick a flag here, a flag here. Every time you pass a crossing, pick a flag, pick a flag, pick a flag, pick a flag, flag, flag. Sorry. Pick a flag before here and then after here, and then just as the transversality condition, the two flags in these positions are exactly identical except the space that it's in this here. So here they have to be different spaces, and everywhere else it's identical. That's what this definition is saying. Now, the way I'm writing it is this condition plus the W naught condition. So this W naught condition in here, so this extra condition in here is going to be the condition that the first flag and the last flag are going to be in W naught relative position. So that's like this W naught. This means they're fully transverse. And this guy, well, that's technically not the braid variety. The braid variety, okay, first need to be said. The same discussion, and how we'll elaborate on that, shows that the moduli of sheaves for this Legendrian is going to be this guy modulo G. Okay. Now, because the first guy and the last guy are fully transverse because of these bogs in here, I can do exactly like in the first example. What did I need in the first example? I put the first one to be 1, 0 and the second one to be 0, 1. So similarly, I can use the GLN action to make this one be the standard flag here, plus the condition F0 is the standard flag. That's the one generated by E1 and then E1, E2, then E1, E2, E3. And the condition that now the last flag of all, this beta is anti-standard. So that's not just anti-standard, but it's W not the standard flag. That's the anti-standard flag generated by EN, EN minus 1, so on and so forth. So these are two conditions that are trying to kill a bit of that G action. So what remains is that you have this variety, X beta, and this variety will have a T action. Because remember, what did stabilize 0, 1, and 1, 0? Diagonal matrices. What stabilizes the standard and the anti-standard flag? Well, you know, the standard flag are upper triangular matrices, the anti-standard are lower triangular matrices. So once you fix those, what you're left is with the diagonal, that's the torus. So this is the Cartan torus. The Cartan torus acts naturally here. And then the analog, the generalization of the assertion that M of lambda for the Hovling was X mod T, now has an analog proposition here that says the moduli of sheaves in such Legendrians is exactly this affine variety. You have to prove this, but this is smooth affine variety modulo this T action. And so that hopefully provides a pretty down-to-earth description. There's tons of literature about how to study these by now, and how hopefully in this presentation we'll start to sort of explore those varieties from this viewpoint, and we'll continue to focus on them. But you know, the hope would be that for any braid that I give you, you're able to do everything with it with a Hovling in detail. Name the space, name the orbits, name the action, name how it looks like, and name how the fillings corresponds to the sheet. And that's something that currently we know how to do, and that's where we're heading. All right, is that all right? Okay, great. Take a break.